Hello, everyone. My name is Daniel. I'm the machine learning platform technical leader at iFood. And today I'm going to talk about how we built a real-time feature store at iFood. Uh, just a quick agenda for today's presentation. First, I'll quickly go over iFood and AI and what's the iFood mission. Then I'll give a quick explanation on what is a feature store and what's its purpose. And finally, I'll delve deeper into how iFood built its feature store. So first, a quick overview of iFood. iFood is the biggest food tech company in Latin America. We're in Brazil, we're in Mexico, we're in Colombia. We have over 30 million orders per month. We're in over 800 cities in all Brazilian states. And we are in over 100,000 restaurants. We have over 100,000 restaurants in our database. And as such, being such a big company, we have AI everywhere. Just some examples. We have AI applied to discovery. So how to recommend restaurants, how to recommend dishes. We have AI applied to logistics and operations. So how to optimize the driver's allocation, how to estimate the delivery time for an order, to find the most efficient route for a driver. And another example, we have AI applied to marketing. So how to optimize the marketing ads, how to optimize the allocation of coupons and vouchers for the users. So having an AI applied to so many different places, it's necessary to have a machine learning platform. This picture here, it's from a really famous paper from Google. It's Hidden Technical Debts for Machine Learning Systems. So what Google was trying to point out is that most of the time when a data scientist is working on machine learning code, she also has to worry about lots of infrastructure problems, such as how to collect data, how to analyze data, how to spin up a serving infrastructure, and so on and so forth. So the goal for the machine learning platform should be to handle all of that. They are represented here in the dark blue boxes. And so the data scientist can worry about the machine learning code. That's the machine learning platform is the team I am the technical leader for. And one of the responsibilities for this team is building the feature store, which I'll be going over today. So what is a feature store? First of all, what are features, right? So features are any kind of data, any kind of attributes that you use to train a machine learning model. So anyone that has played with machine learning tutorial probably has stumbled upon the iris data set, which we are showing here in this picture. And the goal of the problem is how do you identify what class of iris is being represented by attributes such as the petal length and the petal width and so on and so forth. At iFood, we also have features for lots of problems, and they can mostly be classified in three types. So we have state features, for instance. Did the user have or didn't she have she have a coupon at the time an order was made? Another type is aggregate features. So, for instance, what was the average ticket price for a given user in the last 30 days at the moment an order was made? And the third type is external features. So, for instance, was it raining at the time the order was made? And the feature store basically is where you store the features, right? So it's the central place you store and serve the features so anyone in the organization can query for them. They're mostly used by machine learning algorithms, but they can also be useful for other applications. One simple example would be a non-AI logic in the application that you query the average ticket price for a user, so you decide whether to show a high end or a low end list of restaurants. Just a quick overview of the requirements when you're building a feature store. We have requirements that are applicable to all use cases, and some requirements that are mostly focused on the machine learning scenario. So in the general use case, you obviously want low latency, and we'd like to distinguish between access and calculation latency. Access latency is basically how long you take to query for the last known value of a feature. And that's mostly dependent on the database you use to query, such as Redis has really low latency. Maybe Hive database has a higher latency, for instance. And you also have the calculation latency, which is the time you take to update the value of a feature. And that's mostly defined by the processing infrastructure you use, such as Spark. Also, another requirement is access control. So, how do you guarantee some features are readable by some users and some are not? For instance, payment related features, they are really useful when you're building an anti-fraud model, but maybe they're not so useful for a marketing model. So you should be able to control who can access what feature. Versioning also very important, so you can update the calculation code of a feature. You should be able to scale your feature store to handle any number of features on any kind of data without compromising the latency. And you should have an easy API for data access, right? Uh, in the machine learning scenario, we also have a few set of feature of requirements. Um, First of all, you should be able to backfill. For the general use case, you're mostly worried about the last version of a feature. But for machine learning, when you're building training data sets, you're also interested on past values of the feature. So when you create a new feature, you should be able to calculate values in the past. And really related with this, you should also be able to time travel, right? So you should be able to get the value of a feature in the past. For instance, right now, the average ticket price for a given user is some value, but that's probably different than what it was 1 month ago, 2 months ago. So I'm gonna go over how iFood built its feature store. Um, so first of all, I'd like to go to give a quick presentation on the iFood software architecture before I go into the feature store. iFood is going towards a model in which streaming is a first-class citizen. So we have microservices basically for everything at iFood. So every time a user creates an order, makes a payment, every time a driver has her location updated through the GPS sensor in her cell phone, every time a user logs in, and so on and so forth, those microservices, they publish an event to a central bus. We are using a set of Kafka queues for that, and those events in turn, they are consumed by our data lake infrastructure, real-time data lake infrastructure. And this data lake is the source for our feature store, which aggregates the values, creates the features, and store them to the feature store. So first, why we chose to implement the data lake architecture such as this. Like I said, we have a Kafka queue receiving the real-time events. We have the data lake streaming jobs, which really read the events and append them to a delta table, streaming delta table. Why we do that? First of all, Kafka storage is expensive. If we wanted to use a model in which we use infinite retention for Kafka, that would get expensive really fast. Our Kafka queues, they have limited retention. Um, but we also want to have full event history because that enables us to recalculate and backfill the features. Like I said, that's a requirement for machine learning for the feature store for machine learning. And Delta tables provide a cheap storage option. Delta tables backed by an S3 bucket. And also Delta tables can double either as a batch or as a streaming source. So that's a bonus. So in really broad terms, that's the iFood feature store architecture. I'm gonna give a really quick overview on how the data flows here, and then I'll go over step by step on each part. So first of all, we read data from the data lake, the streaming delta tables. They get aggregated and they're used as source for the calculation jobs. The results, they're published to yet another Kafka bus. And data from this Kafka bus, they're read from a set of materialization jobs, which finally write them to the final storage that are used by the end users. They're used for the end users to query for feature values. The first part I'm going to go over, they're the aggregation jobs. That they're showed by the set of parts of the picture. So we read data from the streaming delta table, they are aggregated and published to the Kafka bus. And features, they usually combinations of a data source, a window range, a grouping key, a value, a filter, and an aggregation type. For instance, we could have the average ticket price per user during lunch in the last 30 days. And this data I can get from an order stream. So features are usually a combination of those 6 attributes, and we build the aggregation jobs around that. However, with Spark Streaming, you can only execute one group by operation per data frame or job. And each combination of groupie key and window range results should be expressed in a new data frame. And that means increased cost and operation complexity, because most of the times you change small parameters in one of those attributes to express a feature. For instance, you could want to you should could want to calculate what's the sum of the ticket price per user in the last day, in the last 3 days, in the last 7 days. And for each of these combinations, and you see the code here, it's really similar. We're just changing the window size, but each of those result in a new data frame, in a new job, and that gets you increased cost and operational complexity. Um, so how we worked around that, we created what we call the two-step aggregation logic. What we do, we store an intermediate state for several aggregation types for a fixed smaller window. We call that window step. Then that window step is actually the name that Spark also uses when defining windows. Then we combine those results to emit the result for several window sizes at once in a single job. This also allows us to use the same code and the same job to calculate historical and real-time features. So we lower our costs and our operational complexity. So that picture here, it's a quick example on how we do that. For this example, we're calculating the count of orders per user in a set of windows. We want to calculate it for 1-day windows, 3-day windows, and 7-day windows. So the first row here, we have D-6, D-5, that's coming from the streaming source. For instance, we could have one order made by this user in the D-6, 2 orders in the D-5, 3 in the D-4, and so on and so forth until D-0, which is today, that the user made 2 orders, right? So if we want to calculate the number of orders this user did by 1-day windows, 3-day windows, and 7-day windows, that's a simple matter of combining those intermediate states. The final result of 1-day windows, it's really just a pass-through, right? You don't have to do anything too complicated. Uh, when you're calculating 3-day windows and 7-day windows, it gets a little bit more interesting. But basically what you have to do, you have to combine sets of three days to have the 3-day windows and the full set of 7 days to have the 7-day windows. In this example, we're executing a simple count, but that's applicable to, you can use that to calculate an average, a sum. You can use that to execute a count distinct operation. So that's really flexible. And how do we express that, right? So Sparse Streaming has a really powerful function that is flat map groups with state, that basically allows you to define a really flexible state and a really flexible input and a really flexible output to combine the input data and produce an output data. And by expressing this logic using flat map groups with state, we are able to combine dozens of jobs into one. We have a pseudocode here on how we implemented that, but basically what we do, we read the source, we calculate how much of the state we should actually store, we should actually keep, so we can discard old data and ingest new data. Um, and if the input is in some of the intermediate values, we update the specific intermediate state. Then we go over each of the combination rules we have, and emit and create result rows for that. This is just an example of the input and output for this function. So, for instance, if we have an order being made by the user of ID 1 in the 1st of January of 2020, and we're calculating the number of orders per 1, 3, and 7 days, that one row of input produces 3 rows of output here in this example, that are the number of orders per each of the window sizes. So after we have the calculated values by the aggregation jobs, we go over the materialization jobs, which are expressed by this part of the picture. Data comes in from the Kafka bus, they get read by the materialization jobs and finally persisted to a final storage. And the materialization jobs, they work in the following manner. The result from the aggregation jobs, they are feature update comments. Think CDC or log tailing. That's a really common concept in which you explain how an operation, how a transaction was made. In the case of the feature store, we're usually expressing update some feature for some entity at some row with some value, right? Um, so for instance, if we are reading some update comment for the average ticket price, the last 30 days for a given user, that's expressed here in the first table, the topmost table. And we're storing that to a delta table that would be transformed into the table below, the bottom table. And we use a trick for the delta table storage in which we use a single column for all the features. We call that the feature map. And we combine the merge into operation of delta tables with the map concat function, so we are able to be really flexible when storing the features, right? So for instance, we have in this scenario here, we have the average ticket price in the last 30 days with the value of 25.8 for user 1, and then another operation arrives for the user of ID 2. It's a different feature. That's the number of orders in the last 30 days with the value of 17. That gets you a new row because that row didn't exist before. And then we receive yet another comment and yet another update expression. And that's the number of orders in the last 30 days, but that's again for user 1. So by using merge into and map concat, we are able to emulate an upsert operation for the delta tables. Another really cool feature of this choice of architecture is that we are really flexible on where we store the results for the feature store. So right now for machine learning, we use historic materialization job, which uses a delta table to store the historical feature values. That's what we went through the last slide. But we also use a real-time materialization job that uses a Redis storage for real low latency real-time access. So for instance, when the user is creating an order and you want to have you want to have an estimate on how long it will take, you must be able to get the features necessary for this model really fast. So Redis gets us a really low excess latency. But if, for instance, you know, some user in the company wants to consume features from a different storage, say DynamoDB, ScyllaDB, Cassandra, okay, that's fine. You just plug in a new materialization job reading from the same Kafka bus, and then you're good to go. I'm gonna go over the backfilling jobs right now. So the backfilling jobs, they are responsible, like I said, for producing past values for the features. The parts of this picture here that are pertinent to the backfilling jobs are those ones. So what we do, and I'm going to go over in a more broad level here because they're really complicated and we're kind of short of on time. But what we do, we store in a metadata database. We use DynamoDB for that. We store the creation time for each feature. Um, and having that in hand, we separate the aggregation jobs in two kinds: the normal aggregation jobs, the high story backfilling jobs. The backfilling jobs, they read the source delta lake from the data lake. They read all the events, all the history of events, and calculate and create result rows for the feature up to the moment of the creation of the feature. The aggregation jobs, in turn, they have the creation of the feature, read from the metadata database, and they only emit results for values that arrive after the creation. So basically, up to the creation, the backfilling jobs, they're responsible for that. After the creation, it's up to the aggregation jobs. So that's the architecture of the iFood feature store. We learned a few lessons and a few best practices that along the way, and we'd like to share them. First of all, delta tables, they double as streaming or batch sources. That's really powerful. That gives you a lot of flexibility. Another interesting point it's that optimize is a must for streaming jobs. Streaming jobs create really small files. So if you want to have an efficient reading from the table, you must optimize the streaming delta tables, either on auto mode or as a separate process. And that's kind of a corner case, but when you're starting a brand new job from a streaming delta table, the file reading order, it's not guaranteed. So, and that's even more not noticeable after you run an optimize, which you really should. But if the order of the files is compromised, you're basically introducing an artificial late arrival for your events, and that can be really it can mess up your aggregation jobs if they're not prepared to deal with that. So if the event processing order is important for your job, you should either use trigger.once to process the first historical batch as a whole, or you should create some separate process that reads each partition sequentially and guarantees the reading order. Um, yeah, yet another point. So flat map groups with state, that's really powerful. And but you have a caveat. You have to handle the state management with real care, because if you don't, you can blow up the memory of your jobs. For each batch, which is a kind of sync for Sparse Streaming, it's really powerful too. But one thing we learned along the way is that it can be triggered on an empty data frame. So if you're expecting a non-empty data frame, you should be careful with that. Um, Also, when we're heavily dependent on the merge into delta operation, but you have to be really careful that you're actually getting the partition pruning, because if you don't, you're gonna have a performance drop. Um, Another thing that's important to be mindful of is if you change some parameter between streaming job restarts. And finally, The stream test class, that's, as far as I know, available only for Scala and Java, but it really helps with the unit tests for streaming jobs. It helps to debug the jobs, and it really raises the bar of the code. Finally, some positive outcomes. So, like I said, by using this choice of architecture, we have a unified code base both for historical and real-time features. So that's basically 50% less code than what we had before, because we had separate code for each kind of feature. Also, since right now we have, because of the feature store, we have a single job that calculates both the historical and the real-time features. We could trim down the number of jobs from dozens to around 10. Um, the huge batch ETL jobs, they're substituted by much smaller streaming jobs, but they do run 24/7 all the time. And also Delta tables, they allow for isolation between read and write operations, and transaction isolation between the reading and write operations. So that's really helpful too. And that's it for the iFood feature store. Thank you guys so much. And if you have any questions, I'll be glad to answer. Thank you.